discussion. Okay, so we're going to take a look at. So we're going to start today's class with a history lesson. Okay. I hope this does not upset any of my history, colleagues. I don't think so. I don't think they know what I'm talking about, which means they're not going to be upset. Tech is doing the same usual thing that he's doing. We have no idea what he's talking about to my colleagues. Hopefully, to you guys, it is not the same. All right. So what we'll do is we're going to start with AT&T. Okay, AT&T, which is the first platform that we use, to write. It's the company. Okay, AT&T and Bell Labs is what funded the writing of Unix, but this is not the one that I want to look for. So let me just look up Unix by itself. There we go. All right, so the history of Unix, there are two principal programmers. One is Dennis Ritchie, and then the other one is Brian Carnigan. So one of them actually passed away, I think, days before Steve Jobs passed away. Okay, I think it's just days. Let me take a quick look. I'm curious, and I do apologize for my ADHD because when I need to find something, I go like, I need to find it. All right, so he passed away at the 30th. When does Steve Jobs pass away? So October. Okay, so that's not him. It's the other one. So I think it's Richie who passed away. I lost that link. Hmm? Control Shift. Oh, okay. I did not know that. Okay. So now we go back here. We look at Dennis Ritchie. There you go. So Dennis Ritchie passed away in on October 12th. So it's slightly after Steve Jobs. Okay. But everybody only remember Steve Jobs. They look at the picture of Dennis, Ritchie here and go like, who's here? Right? Well, the thing is, without Dennis Ritchie and his team writing the Unix operating system, that would not be iOS or Mac OS or Linux for that matter. Okay, so what about how does this relate to this class? So he also co-invented the C programming language along with the other guy. Okay, the other guy is I cannot remember either. Carnegie, there we go. So Carnegie and Ritchie were the two co-inventors of C, and the reason why they invented the C programming language was they were trying to write Unix, an operating system, in assembly language, which is doable, okay? But at some point in time, they looked at each other, it's like, do we really want to do it like this? Like, we're trying to build castles out of grains of sand. Okay? They go like, no, we don't want to do this. So they invented the C programming language to make their jobs easier. In other words, the C programming language was never, ever intended as an instructional or educational programming language. Think of it this way. You have two master class carpenters, okay? They look at each other and go like, do we really want to use like a handsaw to do all the stuff that we need to do? They look at each other and go, no. Okay, let's make a circular saw. They look around, okay? They found some motors, some wires and some circular saw blades and go like, okay, we can make one that's really quick, okay? They put something together, okay, which is essentially just a motor attached to a circular saw blade with a cord that you can plug into the outlet. There's no on-off switch. There are no safety features whatsoever. You plug it in, the thing is running already. Okay, so, so the only way to use it is to be very careful. You hold on to the motor as strongly as you can possibly hold on to the motor. You tell the other person, okay, I'm ready. Plug it in. When the thing starts, it's like whoosh, like that. You just make sure that you don't cut yourself, and you have to hold that thing and cut wood like this. That was the C programming language. To a master class carpenter who has been doing this stuff for decades, it's not a problem. Okay, they know the tools inside and out. It's just an easier way for them to cut wood. Okay, get things done. So what happens when this circular saw is now being available at your local Home Depot? Exactly. Yep. Yep, that is our current state when we try to use the C programming language as an instructional or educational programming language. But I think that answers your question as well. Okay. So the whole reason why we have the C programming language was because low-level programming using assembly language was too tedious of a task. So this is just one little abstraction layer on top of assembly language programming. As opposed to many other scripting languages, there are multiple levels on top. You cannot really cut your finger like JavaScript or Java. Even Java is pretty well protected, but you cannot really do a whole lot of damage because it will tell you. It's like when you try to, even if you intentionally try to cut your finger, it will stop and pop up a message with a voice saying you are about to hurt yourself. I need to report this incident, and the ambulance will come anyway. You cannot cancel the medic coming in and just to check on you, check on you, both physically and mentally. So I think sometimes it is good to remember to understand the origin of these things, even though it does not seem to be related, it is related. Okay, because now we start to understand why do we have pointers in C and C++, because pointers are very dangerous. Okay, but the reason why we have those is because it is really just one abstraction layer on top of assembly language programming. So, so it is related to what we are talking about in this class. All right, cool. So let me start with what we are going to do today in the lab so that we can kind of have a context of what we are going to be talking about. So today's lab is this one, which is simple branching and code analysis. So to do that, we need to understand branches and conditional branches. And that's what we'll be focusing on today, are the branch instructions. They all start with J. Okay, so we'll go take a look at the opcode table of those things, and then we'll kind of demonstrate how they work in a typical fashion for this class. All right. So we have two families of jump instructions. So there's one family that ends with an L, okay? So we have J, oh, excuse me, not L. They end with an I. So there's JSI, JCI, JZI, and then there are, okay, I can't really scroll properly here, but this is good, okay? These are the 6 instructions that start with a J and end with an I. So JMPI, JLI, JOI, JSI, JCI, and also JZI. So the first one, which is JMPI, is a unconditional branch or unconditional jump instruction. The other ones are conditional. So the first thing we also want to do is to take a look at, the easy part is the opcode here. So the opcode is, they don't even have XXYY. They don't use a register at all. Okay, so we only see, oh, this one is a 4-0, then we have 4-1, 4-2, 4-3, 4-4, and then finally 4-5 as the hexadecimal representation of the opcode themselves, which means in the microcode in the ROM, the slice or the binary code that dictates what the pathways would be at location 400, 40, 410, 420, 430, 440, and also 450. So those are the locations in the ROM corresponding to these instructions. So we'll start with just the jump I instruction, okay, the JMPI instruction, and we'll take a look at the um, RTL, okay, the register transfer language, which describes it in a very kind of, it looks too simple to be true, okay? We are only doing a PC equals PC, but that would be wrong, okay? Because if I were to say PC equals PC, I'm missing one thing that is really important. which is the asterisk. What does the asterisk do in C and C++? What does it mean? It means dereference, which means I am not overwriting PC with whatever PC already has. I'm going to use PC to look up in the RAM whatever location the program counter is pointing to, the content at that location is used to replace, to overwrite PC, the program counter itself. Okay, so in a typical way, I think at this point you guys already kind of know what I will be doing next. I'll be doing next, which is just start up LogicSim like so, load up the processor, and then we'll take a look at that one single instruction. So we'll go ahead and load the processor. And this time I can do the hand assemble, okay? And I'm going to do a 40 and then a FF over here. All right, so what does it mean? Well, remember, this is an instruction. Okay, let me go back to the description of the instruction, which is here. So this is basically saying whatever immediate operand, the I is here, that dictates the new content of the program counter. Okay, and also from before, let me go to the assembler. Okay, so we'll go ahead and delete the program that we were looking at, and then we do a JMPI to 255. Okay, so JMPI is the mnemonic of jump immediate, and then 255 is telling the jump instruction, okay, so where do we need to go? Location 255. Okay, so when we go to the assemble tab, then you'll see, oh, okay, 40FF, that's exactly what we have in RAM, okay? Because I just hand assembled this entire code, because it's fairly simple to assemble this one. All right, so the next question now is, how does it work? Okay, that's the question, how does it work? So now we go here. I am going to jump all the way to the execute phase of an instruction execution cycle, which means I'm not going to explain the fetch and the decode, and we'll kind of skip to the execution phase, which is, let me count, 1, 2, 3. Okay, 1, 2, 3, 4, and that would be the fifth control T. Okay. All right, so so the first control T is fetch, and then we increment the microcode pointer, then we increment the program counter, and then we decode the instruction. So this is the execute phase for that specific instruction. How do we know? Because when we look at the microcode pointer, it is based on the instruction register, except it has one more zero padded to the right-hand side, and the clock is going to be a rising edge. That is how we can tell that we are about to execute an instruction, okay, which is already decoded. This is right after the decode. So now we're going to do the usual analysis. We look at all the registers and say, okay, who is active? Who is going to be updated? The instruction register not going to be updated. We can forget about it for now. The register bank is also not active. In other words, nothing in the register bank is going to get updated. Okay, we can forget about it. If we look at RAM, we go like, oh, okay, RAM is selected, which means it is enabled. It's going to do something. And then we look at the program counter. We also see that it is about to update. So we only have two components that are actively trying to do something, and we have to figure out what they're going to do. Is that okay? There are only 5 components altogether that we have to initially start with, which means it shouldn't take long, okay? And then once we identify one of them, it's already enough, okay? So which way do you want me to start with? Because I can start with the PC, the program counter, or I can start with RAM in this analysis. You can, hmm? Okay, so we want to start with RAM. Okay, so we'll start with RAM. So when you look at the RAM component, in this case, you look at the select, okay? Select is lit, which means the RAM component is enabled, which means it is going to do something, okay? All right, so as soon as you know the RAM component is going to do something, I think the next natural question is, what is it going to do? There are two things it can do. You can either read from RAM or you can write to RAM. So the question is, are we retrieving the content at a location or are we changing the content at a location? So how can we find that out? The LD port, that is correct. So we look up the LD port, it is a bright green, and if you hover, it will also tell you that if it is a 1, the memory is in an output mode, which means it is retrieving the content of a location, and then the content of that location becomes the output of port D. Okay, so what is the next question? Now that we know that RAM is active, we are trying to read a location. What is the next question? Go ahead. Hmm? Where does it go? Okay, very good. Okay, we can do that. Because those two questions, we can address one or the other first. It doesn't really matter because there are two questions that are equally important. One is who's telling me to look at location 01? That's one question. The second question is why do we care about what is at location 1? Who's trying to read it? So those are two separate questions. You can ask either one first. Okay, the ordering does not matter. So, as you suggest, we're going to answer the question of who cares about the content of location 1. So now we follow this trace here. It goes all over the place, right? But we already know that the instruction register does not care, right? We also know that the register bank does not care. This is an output of a demultiplexer, which is turned off, so it's not really a big deal. So the only thing left is this connection here. So this is input 1 of a multiplexer. The multiplexer does have a select of 1, so that means this wire, which is representing what the data port of RAM is outputting, is connected to the output, which only goes into another multiplexer. So when you look at the other multiplexer, it also has a select of 1, and this in fact is input 1. So that means this is going to, oh, it's going to the program counter. It's going to the D port of the program counter, which means whatever is at location 01, which is FF in hexadecimal, is going to be used to update the program counter itself when the clock is rising. Okay, when we have a rising edge on the clock. Is that okay? That's the first part of the analysis. The second part is why are we addressing location 01 to begin with? So that means we have to track down the A port. When we track down the A port, it's coming out of a multiplexer. The multiplexer is configured to be a 1. So that means it is coming from, the program counter itself. So that means the program counter is telling us which location of RAM that we need to look up. Take that content, okay, and use that content to update, guess what? The program counter itself, okay? So that is why we document it in this way. So when we go back to the opcode table, the RTL reflects exactly what the circuit is trying to do. The program counter drives the address bus of RAM. The RAM is outputting the content at the location that the program counter is pointing to, and the program counter is using that output to update itself. Are we good so far? Yes. Yes. But there's more, okay? So what is more this time is I want to know why PCMux is a 1, okay? I want to explain why this is a 1. Then you go like, well, that's coming straight off the ROM, right? No, it does not come straight out of the ROM. Because when we highlight this wire here, you can see all of these are highlighted, but not anything that is directly connected to the ROM. So that means PCMux is not coming out of the ROM. This is PCMux as a tunnel. This is also PCMux as a tunnel. So you can see that PCMux is actually the output of this multiplexer. So now the question is, ugh, that looks ugly. This is one of those, this is one of those multiplexers that has a lot of inputs, right? So you go like, okay, well, since it's a multiplexer, we have to look at the select. The select is 111, which is 7. This is input 0, input 1, all the way to input 7. And input 7 is like, this is really dumb. It just connects to a 1. Yes, this is how we say, yeah, let's make PC mux a 1. Is that okay? So PC mux, double mux, is actually coming out of the ROM because when you highlight this wire, it also highlights, I think you can barely see it here, but it also highlights this wire here. So PC mux mux in fact is coming out of the ROM because microcode data is coming out of the ROM. Okay, so now we have explained why or how the ROM is basically coordinating everything. It's telling RAM to, hey, wake up, we need to read from you. It is telling the program counter, it's like, okay, you wake up too. You're gonna have to update. It's also telling the multiplexer here that is selected by address mux and go like, you have a job too. I need you to connect input one to your output. Okay, so those are the directions coming straight out of the ROM. And there's also one more. The ROM is also, telling this particular multiplexer here and go like, yeah, we would like your input 7 to connect to the output. That will in return be using controlling this multiplexer so that we complete the path from the data output of RAM to the input of the program counter. So the ROM is really doing all the coordination. Okay, so now the question is, why do we have this multiplexer here? This looks really awfully unnecessary. Okay, well, it is necessary because when you look at the other wires, this one is easy. Okay, these two output um, 5 and 6, they're both coming from 0. Okay, that's the way we can say, okay, PC mux, I want you to be a 0. But the other 5, these 5, they are kind of interesting. Where do they come from? Hmm. It's coming from not the ALU, but the flags register. They are the output of the flags register. So it's like, oh, okay, that is a little bit strange. We have never really talked about the flags register. So, but before we move on to talk about the flags register, are we understanding the jump instruction itself? Okay, the rising edge is going to change PC to FF. Okay, so let's go ahead and do it. Okay, let's go ahead and do a control T, and we can see how the program counter is now FF. Can someone remind me again, what is the job of the program counter? It controls where we fetch the next opcode from the RAM. Yes. Yeah, that's okay. That's okay. So it is the one register that is used to tell us where to fetch the next opcode. So this means the next location where we're gonna fetch the next opcode is location FF. Okay, we are continuing execution at location FF from location 01 because it was a 0 before, now it is FF. Then the question is, what about location 02, 03, all the way up to FE? We skipped all that. Hmm? The program counter is a pointer. It is an action to continue execution at a location that we specify, so it's not a pointer per se. Yeah. The label tells us is a symbolic way to tell us where we need to go, but the action, which is the jump, is really just saying, okay, you want me to go to a certain location to continue execution. Where do you want to go? Where do we need to go? So that's the jump instruction. Are we good? You could. Yep. Yep. You could. Yes. The whole idea is you can skip certain things or go back to a previous location. Yes. It Well, it doesn't decide to skip it. It's because the instruction is to skip it. It's because the program literally is just that. So the program says, let's continue execution at location 255. So all the other stuff, even if I have stuff here, it's going to be skipped. Yeah, because this basically just goes like, okay, forget everything in between, just continue execution at location 255. Now, why are we skipping to location 255? There's no particular answer to that one because I'm just using this as a sample program. Yeah, so there's no reason to the why because the entire exercise is to explain the how of how this can happen. You mean the assemble view like this? No, the 40 is the opcode. The opcode is determined by the opcode table on row 9. So that's what the opcode is. And then the FF is indicating, where do you want me to branch to? So the FF is in a sense a pointer. So to get to your point, this FF here is essentially a quote unquote pointer pointing to where are we going to continue execution. So am I addressing both of your questions? Correct. Yep. The 40 is the opcode. The 40, we can still see the significance of the 40 because the 40 is what led the microcode pointer to become 400, which then use this particular bit pattern to establish the path that we saw. The path that we saw has to do with this multiplexer, switching in a certain way, this multiplexer switching in a certain way, and also this multiplexer switching in a certain way. It has to do with the program counter being enabled to an update. It also has to do with the RAM being configured in the read operation. Yep. So that's the job of this particular location is to orchestrate the rest of the processor to have the right pathway and also have the right components waking up to do the right thing. All right. So are we good so far? Okay, so we are now going to have a falling edge. The falling edge is going to increment the microcode pointer to location 401, but 401 is 2 followed by all zeros, which means it's going to reset the microcode pointer itself back to 000, okay, like so. So that means now we are going to location FF to try to fetch the opcode over there, which is a no op. Okay, which also means after this we're going to roll all the way back to location 00 and the whole thing starts again. So this is essentially a huge gigantic loop, or you can call it a very short loop because we're skipping a whole bunch of locations, go all the way to the end and then wrap around. Hmm? Hmm? Okay, 4 iterations of, so it goes to locations. Oh, okay, I see what you mean. Well, actually, if you are looking at the actual locations that we have accessed or we will access, it's only 3 locations. Location 00 for the opcode of JMPI, location 01 for the FF. So even though the program counter will point to location 02, we never really access it. We did not read it. Yes. Oh, okay, with that no op. Yes. Yep. But in this case, we did not have that no op because, oh, okay, yeah, we did not. So if we, yeah, so you can see how it's jumping back to that location. Yeah. So with this one, I have to slow down the tick frequency probably to maybe 16 hertz. And if we enable the ticks, you can see how it is looping visibly. Yep. Cool. Cool. All right. So do we have any other questions about the unconditional branch instruction, which is JMPI, jump immediate? So we good with that? All right. So once we're done with this, then we can go ahead and talk about conditional branches. Okay, because once you heard about unconditional branch, your brain, your mind will automatically ask the question of if this is unconditional, what is conditional, right? So there's a conditional branch. So the first thing we're going to do is to take a look at the one of the conditional branches. We'll take this one, okay? So this one has the opcode of 44 because 0100 is 4 in hexadecimal. So this is really just 44. The mnemonic is JCI. Doesn't seem very impressive, right? And then the description in English is jump if and only if C. Okay. So now the question is, what is C? C is carry. Okay. So C is carry, which is basically what we know as K8 and also T8. Okay. So now you have to kind of go back to binary addition and subtraction. And remember what exactly is K8 versus T8. Okay, K8 is applicable for addition, T8 is applicable to subtraction. It is the overall carry or borrow in a binary operation. Okay, so what we'll do now is we'll take a look at some add instructions so that we can actually set stuff up properly. So we'll go ahead and go back to the assembler and we'll just go ahead and change the program a little bit. We'll start with add instructions. So we're gonna say add BD and that's it. Okay, that's the whole thing. So you go like, well, but they're gonna start with zeros and this is not gonna be useful. Yeah, we'll fix all that. So add BD, if you look up the opcode table, if I want to hand assemble this instruction, then we have to look up the add row and oh, okay, just skipped it right here. Okay, so this is add. It starts with an 8 because 1000 is an 8. So because I said BD, right? So B is a 0 1, D is a 1 1. So that means it is a 8 7 in this case. Okay, so 8 7 is the opcode. Okay, um, and then yeah, so 8 7. That's it. Okay, it doesn't need anything else. So now we go back to the processor. Okay, and then we reset the whole thing. Control R. And then at location 00, I will say 8 7. And then at location 01, I say 01, which is the halt instruction. Okay. So are we good so far with why I put those two specific bytes in RAM? 8 7 is for the add instruction, adding register D to register B. 01 is just a halt instruction so that the program stops execution after that point. Are we good so far? All right. So adding 0 to 0 is not really a whole lot of fun because we can't even see the result. So we're going to go into the register bank and say, okay, let's make this a little bit more exciting. So we go like, register B, I want you to be 8E. And the register D, I want you to be, uh, 4 7. Okay. So now we look at this and go like, okay, let's do some hand calculation just to make sure that we know what is supposed to be in register B when this is all done. So let me go back to the text editor. Okay, this is from the previous class. So we'll start a new document. Okay, so we have 8E added to 4 7. So I'm going to do the full addition thing. And the carry is going to be K0 is going to be 0 here because we are not stacking the operations. So now we go like, okay, what is E plus 7? E is a 14. 14 plus 7 is a 21. But since this is in base 16, so 21 mod 16 is a 5. Okay, with a carry of 1. 5 plus 0 is just 5, so we stash a 5 here. 8 plus 4 is what we know as a 12, but in hexadecimal, it is a C. C plus 1 is a D. And then it does not have an overall borrow. Okay, that doesn't really achieve what I wanted to do. That's okay. Yeah, it's okay. All right, so what we'll do, okay, this is already set up. So what we can also do, in order to see a change, is to go to the flags register and say, okay, even though by default all the flags are zeros, we're gonna turn them all on. Okay, so I'm just injecting those values, okay, as the start condition of this program. So the flags register has 5 bits, okay, and you can only enter the values in hexadecimal. So that means it's going to be a 1F because F is 1111, and then the extra one on the left hand side is the dangling bit 4 that does not belong to the least significant hexadecimal digit. Is that okay? All right. All right, so with this all said, now we can go ahead and do the actual execute the instruction. So once again, to execute the instruction, we start looking at the microcode pointer. We have fetch, we have increment. Oh, that's fetch. And now we have increment the microcode pointer, increment the program counter, decode, okay? And now we can take a really quick look at the add instruction. This part should be somewhat boring because this is how we started the whole discussion, okay, is to use one of the arithmetic operations. So now we go like, okay, we see that something in the register bank is going to update, go into the register bank. Okay, register B is going to be updated, okay. So now we have to go back out, find out how it is updated. So we track down this multiplexer, it is enabled, and then the select is a 1, so that means we have to track down this thing. It is coming out of the ALU, right? So we go into the ALU, find out what is going on here. The operation select is 000, so that means we're using the adder. Okay, so let me use so we're using the adder, which is here. So that means we have to know what we are adding. Okay, so we track this down. It is coming in from in1. Oops, sorry. And then we track down the other one. It is coming from in2. Okay, let me click on it. So this is coming from into. So we have to go back out and find out, okay, where is in1 and in2 coming from? This is in1. It is coming out of this demultiplexer, which is enabled, and then the select is 1. Okay, so that means we are really connecting the input to output 1 over here. So now we go back into the register bank and ask, who is outputting to output 0 of the register bank. We track down this wire. It is coming out of this multiplexer. This multiplexer has a 0, 1 as the select. That means input 1 is selected to connect to the output. Okay. Now we see that register B is going to in one of the ALU, for the add operation. Okay, now we go for the second one. We track down into, it's coming out of this multiplexer. This multiplexer is selecting input 0, which is this wire over here. And then this demultiplexer is in fact connecting the input to output 1. Good. So now we have to track down who is outputting to output 1 in the register bank. This is the output pin, right? And then the select is a 1, 1, which means input 1 connects to the output. We track down this wire. It is in fact register D. Okay. So that's a really fast version of tracking down all the connections, right? So I do not expect you to do it nearly as quickly as I did because this is new to you, but I do expect that you can do it, okay? Given enough time, you can figure out this stuff, right? Okay. So, not too surprising, right? So register B is going to be updated with what is it? This is D5, right? So D5 is in fact what we expect it to be. Cool. But the focus of this entire thing is not even what we're going to store in register D, but what we're going to store in the flags register. Okay, because you can see the flag register for once is enabled. Okay, with all the instructions, almost all the instructions that we have talked about, the flags register is like, does not concern me. No, I don't care about this one. But now it is enabled, which means it's going to be updated. So anytime anything is going to be updated, you have to ask, how is it going to be updated? So the D port connects to flags out from the ALU. We go back into the ALU. Okay, so now let me get this one out of the way. We don't need that anymore. Here we go. All right, this is flags out. Okay, it is merged, or it is, yeah, it is merged from 5 different wires. There's C out, Z out, S out, O out, and some funky gate, that is combining the S out and O out. Okay, so let's figure out all this stuff one by one. What is C out? So C out is, mm, let's see, nope, not here. C out is right here. So it is the output of this multiplexer. This multiplexer is using the very same select as the OPSEL or the op select, which is 0, 0, 0 at this point. So that means C out is actually connected to the C tunnel. The C tunnel, on the other hand, is connected to this C tunnel over here, which is the overall carry of the addition, which is a 0 at this point. Why is it a 0? Because we actually did the calculation ourselves and we make the same conclusion. I think it's the last of the tabs, like that one. See, that's the 0 that we are looking at here. Okay, so now let's take a look at all the other ones since we're here already. So what about Z out? Okay, so Z out is up here. Okay, this is our Z out. So what is Z out? Z out is the NOR of all the individual bits of the output of whatever operation that we are trying to do. So is the sum that we are calculating 0? You don't even have to remember the whole thing. All I need to know is, was it a 0? Nope, wasn't a 0. In fact, I know exactly what it is because I can read the lines here. So the output of the adder is technically a 1, 1, 0, 1, 0, 1, 0, 1, right? So that means it's not a 0. But because this is a NOR operation, so without a bubble, okay, it means if at least one of these wires is bright green, the output is going to be bright green. It's going to be a 1, right? So the only time without a bubble that I can get a 0 as an output is when everything is a 0, right? But because of the bubble, it is negated. The output of the OR gate is negated, and that's why it's called a NOR gate, is a negated OR gate. So that means the only time Z out is going to be a 1 is when everything going into the input are zeros. And that's why it's called the Z flag, because it is the 0 flag. Okay, when the result of a computation is 0, that is the only time the Z flag is going to be a 1. So not surprisingly, this time it is a 0 because the result of the sum or the addition is not a 0. Okay, so that explains the Z flag. What about the next one here? This is the S flag. Okay, so what is the S flag? S stands for sign. Okay, it is defined exactly the same way as the sign flag in binary comparison. Okay, so if you say, I vaguely remember the sign flag in the binary comparison module, not bad, okay, because you are allowed to take any notes and bring any notes and print anything you want in the next exam, right? All the exams, in fact. So if you vaguely remember that, okay, not bad. If you know exactly how the sign flag is defined, which is, oh, it is the most significant bit of the result of the operation, even better, right? So, but we can actually verify that over here too, because once I have the tunnel already highlighted, I can quite easily track down where it's coming from. It is coming from here. There's a little splitter here. There's a tiny little 7 here. So that means whatever this node is, we are only extracting bit 7 out of that thing, and that becomes S out. Okay? Mhm. No, it does not determine whether it's signed or unsigned. It just reflects the most significant bit of the result. You can use it in whatever you can use it or not use it depending on the context. Okay? So that's the best I can explain is it is an output, okay? It is available, but whether it means anything to you in the context of what you're doing, we don't know. Okay? That depends on the context. All right, so that explains the third flag, and now we move on to the fourth flag, which is flag 3. It is O out, okay? Of all the flags and all the bits that we have talked about, only one of them starts with a O, which is overflow. Very good. So because this is an addition, the way the overflow is defined is a little bit different. So basically O out is here, we are using input 0 to become the output. So this is actually the way we compute overflow in an addition. So does it make sense? Okay. So this means if both of these are zeros and this one is a 1, then we have an overflow. Then you ask, what is S1? What is S2? What is S out? Well, we know what S out is already. It is the output, it's the sign bit of the output. S1 and S2 are defined over here. So they are basically the sign of the first input and also the sign of the second input, X and Y, basically. Okay, so in an addition, this particular AND gate is basically saying, it's basically asking the question of, do we have a situation where X and Y are both non-negative, but the result is negative in an addition? Okay, tell me whether that makes sense to you or not. X is non-negative, Y is non-negative, but X plus Y is negative. Does that make sense? No, it does not make sense, and that's why the AND gate is going to output a 1 in that situation. The second AND gate is doing exactly the opposite. In an addition, does it make sense that the first X is negative, Y is also negative, but X plus Y is not negative? That does not make sense. Okay, so we have an overflow too. So by combining both of those output with an OR gate, this is basically the same thing as overflow for subtraction, except it is applicable in an addition, in a signed addition. This tells us whether there's an overflow or not. So in the example that we are looking at, do we have an overflow? We do not have an overflow. You're correct. We do not have an overflow because this is negative, this is positive, negative plus positive ends up with a negative, does not have an overflow. That is correct. All right, one more, right? There are 4 flags, 5 flags. This one, okay, this one I don't even bother to name it, but what exactly is it? In other words, what are we doing with the sign flag and the overflow flag with this gate over here? It's exclusive OR. So that's our L flag. Okay, so the L flag is bit 4 of flags out. Is that okay? So when we look at these 4 bits over here, this is the carry flag, this is the Z flag, this is the sign flag, this is the overflow flag, and now this is the L flag. All right, so now that we know where the 5 flags are coming from, what are we doing with those in the main circuitry? In other words, where is this going? Okay, let me go back here. This is flags out. Okay, that wire. I cannot click it easily because it wants to put a big circle over the chip. There we go. So this is going into the D port of the flags register. The flags register is enabled. So that means when this clock goes up, when we have a rising edge, flags is going to be reflecting all the flags from the add instruction. Are we good so far? Okay. So now we do a control T and we see that, oh, it is changed. Excellent. Are we good so far? All right. So the carry flag is actually cleared at this point. The L flag is a 1. Okay. And the program is about to get to the halt instruction. Is that okay? All right. So right now, the most important part is, are we understanding how the flags register works? How does it get the value? What inside the ALU determines the flags, the value of the flags? Okay. All right. So at this point, I'm going to change the program. Okay. I'm going to change the program so that I have a conditional branch instead of a halt instruction. So now we have to go back to the we have to go back to the opcode table, and I want a JLI in this case. Well, actually, I can use not just the JLI. Let me take a look. This is a 1, 4. So that means the sign flag is a 1. We can use a JSI. Okay. So I want to use a JSI instruction. The JSI instruction is specified here. So it has an opcode of 4, 3. And then I have to determine where I want it to go. Okay. Let's just say that it will go to location 255 again. Okay. So I go back to the program without reassembling or using the assembler. I just go like, I'm gonna wing it, which should not be a surprise to any one of you, right? So we do a 4-3 here, and an FF over here, and then put the 0-1 over here. In other words, I have just changed the program when it is executing. It is not possible in an actual environment, but since this is a simulator, I can tweak things all I want, between the clock edges. Are we good? All right. So now we're going to finish with the add operation. Okay, so the add operation it is done because we can see how register B is already updated to a D5. So now we have a rising edge. Um, yeah, we're gonna have a falling edge. Excuse me. We're gonna have a falling edge, which means the microcode pointer is gonna go to 871, which means it's gonna reset back to 000. So Control T. We're ready to fetch the next opcode, and just in time because I just tweaked it. It was a halt instruction. Now it is a JSI instruction. Okay. So now we go through the uh, fetch, increment, microcode pointer, um, increment program counter, and decode. There we go. Okay. So now we are done with decoding. We are about to execute the microcode corresponding to JSI. Okay. So now we want to find out, okay, what exactly is going to happen this time? So quite a few things that are kind of a repeat of the JMPI instruction. So let me just kind of point out all of those. We see RAM is selected. Okay, it's actively doing something. It is being read. Okay, cool. Where is the D going to? Okay, it's going to this multiplexer here, and then that multiplexer goes over here, and this is a PC mux. Oh, this is a 1 this time. Okay, but we'll do something here. Why is this a 1? Why is PC mux a 1 this time? How can we tell? You cannot visually tell because PC mux is the output of a particular multiplexer, which is this one here. So now you go like, oh, wait, this time there are 3 reasons why the output of this multiplexer can be a 1. So you cannot visually tell why. The only way you can tell why is to look at PC Mux Mux. PC Mux Mux is now a 0, 1, 0, which means 2. So this is input 0, this is input 1, this is input 2. This wire is the reason why PC Mux is a 1, which is also why we are using the output from the data port of RAM to update the program counter itself. Is that okay? And if you guys are asking, so I don't see anything that is conditional. Why is this called a conditional branch? Well, let's go tweak something. So we're going to go to the flags register and say, well, the sign flag is now a 1, and the sign flag being a 1 is the only reason why this is a 1. So let's turn that sign flag into a 0. So that sign flag is this 4 here, which means if I put in 1 0 up to into the flags register, this should become a 0. Does that make sense? Okay, so let's do it. Okay, so I'm going to click here, type in 1 0. Ooh, look at this. It is now a 0. So what if it is a 0? If it's a 0, it just increments. If it is a 1, then it will take whatever the RAM is outputting to update itself. That is how a conditional branch works inside the processor. Okay. Do you guys want me to change the flags register back to 1 4 just to take a look? Yeah, let's do that. So we change it back to 1 4, and you can see how PCMux is now a 1 because this wire is ultimately connected to this wire through the multiplexer. So when we change the content of the flags register for that particular bit, that changes also PCMux over here. But this PCMux is selecting which one of the input of the multiplexer is going to be used to update the program counter. So what are the two choices? This is the one coming from the D port of RAM, which is what we tell it to branch to if and only if the sign flag is a 1. This one, on the other hand, is just, let's just add 1. We'll continue with whatever is next to us. Are we seeing how it works? Okay, very good. So as it turns out, this is the only way to make decisions when you're programming in assembly language. There are no if statements. There are no ampersand ampersand. There's no logical and. There's no logical or. There's no logical not. Okay. You don't have a do while loop. You don't have a while do loop. While loop. You don't have conditional statement like if. This is the only way to make a decision. So this is one interesting aspect of the lab that you're going to be doing today. You won't be diving into the details like this. In other words, I'm not going to give you a gigantic multi-part select, multiple choice question like on Monday. So this one doesn't have it, okay? But what it does have is I want you to tell me how many times a particular instruction executes. So we're going to use the remaining amount of time to address that, okay? So you might need to take some notes, maybe not, okay? It's up to you. So what we'll do is I am going to write some code here, and then we are going to trace a part of it. Okay, where's my browser? There we go. No, that's not my browser. There we go. There we go. All right, so we go back to the assembler, and in fact, I'm going to use my text editor to write the code. Loop.ttpasm. Start with the no op instruction, and then we'll do a label L1 over here. Maybe, yeah, L1 goes here. And before that, we also want to put some. I have no idea why it's thinking no op is a problematic thing. Weird. It doesn't like it. All right. LDIC with 2. Somehow it thinks there's a logic error here or syntax error. Hmm. I'll fix that later, figure out why it's doing that. All right, so now we have a label L1, and then we can say one more LDI, B1, subtract B from C, and then we do a JZI to label L2, otherwise JMPI back to L1, and this is L2, where we have a halt instruction. Okay, I have no idea why the syntax highlighting is having a problem. Okay, deal plead requires. Oh, okay, I know why. Because I was using the wrong editor. I'm supposed to be using nvim, not vim. The N stands for Neil, so this is supposed to be the new Vim instead of just Vim. There we go. Everything looks good now. Okay, excellent. All right, so let's check out what this program is going to do. Okay, based on what we have learned up to this point, we actually have enough information to figure out what it's going to do. Line 2 doesn't do a single thing. It just needs to be there in order for me to use the tool that I might use today. Line 4, okay, so just to document it, right? C equals to 2, that's all it's going to do. C equals to 1, that's all it's going to do. This is, oh, B, that's right. Yep, there we go. So this one says C equals to C minus B. Oops. Ah, can't type. Okay. And this one means it'll jump to L2 if and only if C is 0, which is basically the result of the previous operation. And this one is saying, okay, jump to label L1. All right. So that's basically what the code is trying to do. So what is it going to do when we execute it? So I'll just dry run it. Okay. So the first time we get to here, C is going to be, it will become 1 because 2 minus 1 is 1. 1 is not 0. It's going to skip this one, go straight to JMPI to L1, continue execution at label L1, and then we'll subtract again. So C is now a 1. You subtract 1 from 1, it becomes a 0. So the JCI says, oh, okay, the Z flag is a 1. Let's go to L2. It goes to L2, which is a halt instruction. The program ends its execution. Is that okay? Yeah, basically it's a for loop. Yep. It's not exactly a for loop. It is a for loop or a while loop where the condition itself is the side effect that you also want. Yeah, we'll talk about that later. It's not super important. So if we change this to some larger number, let's say 14, okay, that means it's just going to go through the loop a few more times, right? So now the question is, how many times am I going to land on the instruction on line 7? In other words, how many times am I going to execute this instruction on line 7, the subtract instruction itself? You go like, is it 14 or is it 15? Or is it 13? So that's what we want to find out. Okay, so let's just say that that is what we want to find out. So now we put this program, okay, to the assembler, and then we'll go ahead and try to run this code and use a tool to help us figure out the number of times that instruction executes. So this is the way that I do it. Obviously, you don't do it the same way in Windows. Okay, go back to the assembler, which is right here. Get rid of the existing program, paste this new program in, wait until everything is all done. Mhm. All right, it's all done. This is the RAM code. Go to File, go to Download, get to CSV, and we'll call this loop.csv. Go back to the processor, Control R, reset the whole thing. Go to the RAM component, right click, load image. It's going to be loop.csv. So now we got the program. So now the question is, how can I possibly count the number of times a particular instruction executes? So now we go to here, go to the Assemble tab. So in the Assemble tab, because this is the instruction that I'm interested in, I want to know how many times this particular instruction executes. Okay. So the important part is not so much the opcode itself, because in a program there can be many instructions of exactly the same opcode, so you should not be relying on that. What is important is the address. It's the 05. Okay. So now the question is, okay, now that we know, we want to know how many times we fetch the instruction at location 05, how can we do that? Well, there are a few ways to do it. If you want to use a lot of time, and because you like to look at the simulator and click Control T on the keyboard, you can do it that way too. Because what you can do in that case is to count the number of times that the program counter is at the location that you want, and at the same time you're fetching. So if you're fetching, that means the microcode pointer is going to be a 0, and you're about to have a rising edge. Okay, so you can do it that way, which I do not recommend because it's painful. Okay, but some people like pain. I cannot say anything about that. So if you guys want to do it that way, it is your choice. All right. But as it turns out, Logisim comes with a really nifty feature. You can go to Window, and I need to remember where I can find it. It's under Simulate, and go to Logging. It has logging capability. So once you get to logging, the first thing you need to do is to choose what you are going to log. Okay, and these are your choices. So you can log the A output pin, which is really just the address pin. You can log the D pin, which is the data pin from the RAM. You can log the flag register. You can log the halt, output pin. You can log the OP fetch pin. You can also log the program counter. Hmm. Okay. So let's take a look at the OP fetch pin. The OP fetch pin is right here. So what makes the OP fetch pin turn into a 1? So let's check out the OP fetch pin. It is the output of an AND gate. The input to the AND gate is the clock pin and also the enable of the instruction register. The only time the instruction register will have this enable being a 1 is when we're fetching. Let me say that one more time. The only time this wire turns into a 1 is when we are fetching. But we also want to make sure that it is a rising clock, okay, just to be sure, okay? So when the clock is a 1 and also this enable is a 1, that's why that's a fetch operation, okay? So that's what OP fetch is about. So now we go back. Oh, okay, I got rid of that screen already. Have to go back in, go to logging again. So I'm going to pick OP fetch as one of the things that I want to watch. And I think the program counter is going to be useful too, because that is telling me where I'm fetching. Okay, all right. By default, everything is in base 2. If you don't want it to be in base 2, you can change the radix to base 10. I choose base 16 just because the assembler is everything is in base 16. So I would choose base 16. All right, but we're not done yet. Because when it's logging, you have the choice of logging into an internal table, which means when Logisim crashes, you lose that. Or you can log into a file, which is what I would do. Okay, so I would do it into a file by selecting the file first. So inside the temp folder or wherever you want the log file to be located, I'm going to call this one, count1. Okay, and the extension is whatever you want. Okay, CSV, TSV, TXT, they all work. So we're just going to use TXT here and then click Save. So at this point, I can now close the window because when I run this code, it is going to send all the logs to the file. Okay, and it will stop, when the execution get to the halt instruction, because at that point it's not gonna fetch anymore. All right, so we'll do a Control K, so that the whole thing can do it on its own. And it is 14 times, so it's going to take a little bit because I didn't use the maximum clock speed. So we're going to wait until the halt pin is a 1. Or did I make a mistake? Oh, no, we're good. Okay, so now we have stopped. We do a Control K to stop the clocking. And now you can use any editor that you like to use to examine the file that we just created, which is called what? Count.log, I think, .txt, I think. Yeah. Okay. So I'm going to use my own tool. Okay. You can use whatever tool you want to use. It is called count.txt. Or is it something else? I cannot remember. Huh? Count one? Okay. Count one .txt. You go like, whoa, look at this. Okay. The whole thing has 166 lines. What are we going to do with this? What are we going to do with this? That was not a rhetorical question. The first column is OP fetch. Okay. Whenever OP fetch changes, it will create a new row. The second column is the program counter. Whenever the program counter changes, it will also create a row. Okay. So you go like, okay, OP fetch, seems to be going on and off quite a bit. But what location are we looking for again? 0, 5. Okay. And that's the second column, right? So that means only these are of interest to me. Okay. So this is a 0, 5 with a 1 of an OP fetch. This is one execution of that instruction. And then go like, okay, here's another one. And you go like, here's another one. Okay. So that means you might want to choose an editor that allows you to search. Okay, so in this case, I can search with one space. I think that's a tab actually. So space tab 0, 5. And now we can actually highlight everything like that. So we have, okay, go back to the first one. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14, because this is going back to the beginning. Is that okay? That's one way to do it. For those of you who use Linux, Mac OS, or something like that, you can also use grep. So you can say grep and then specify we want a 1 and then a tab character 0 and then followed by 0, 5. And then you go specify which file. Okay, it's my count1.txt. Why is it not working? It is 1. Okay, there we go. So it gives you all the lines. But if you're lazy like I am, you can pipe that to WC, which is word count. It will give me 14 as the number of lines of the previous command. Do you have to use it this way? No, I'm just showcasing why Linux or command line interface is actually quite useful a lot of times. Okay, so what if I change the program and I want to do another count? Okay, so let me go back to the program and say, this is not the program that I want. I want to change this to a 16 or so, okay, like so, right? Save the file, okay. Reload the program into RAM, into Logisim. So yeah, basically what we are doing is we are just changing this in 0E, the 14 to what again? I can't remember. 16, okay, which is a 1, 0. So we are basically just changing this to a 1, 0. And I need to reset everything, change the clock to a 0 first, and then click this reset button so the program stays here. So now I can continue to trace. Okay, Control K. In fact, this time I want to maximize the clock speed because there we go. So we're all done. Control T again, Control K, sorry, Control K again, and then we go back to the text file. Okay, and then we go use the same command. It's like, whoa, tech, something's not right. It's supposed to be 14, supposed to be 16 this time. Why is it 30? Because it appends to the file. Okay, every time you run with the logging turned on, it will only append to the file, which is not what you might need to do for the homework assignment or for the lab, because for the lab you have to restart the whole thing. Okay, so this is how you restart the whole thing. I believe the instructions are in the lab instruction itself, but I just want to show you how to do it just so that it is easier to remember. So what you need to do is actually go to the log again. Okay. Anytime you want to restart the whole thing, you go to select here. Even if it's the same file, you can do it. You basically re-specify exactly the same file. Logisim will detect that you want to send output to exactly the same file, but it will give you two options. You can either overwrite the content from from scratch. It will basically delete the file and start all over, or it would append. In your case, for this lab, you want to overwrite, okay, because we need to reset the counter. So you just type overwrite like so, then we can restart the whole thing, okay? So this time I turn the clock back to 0, reset everything else, but I maintain the content of RAM, and then we do a control K again, and then we are all done. And then this time, when I go back to count the number of times, it is now back to 16. So it is really important not to append to the file when you do the counting. Are we good so far? All right. I think that's the last bit of information that is important for your homework or for your lab. So, all right, so let's go ahead and get the lab started, or so that you can get started if you want to. So this is the lab for today, and then the password or the access code is JOY, Joy. I'm just making fun of the instruction JOI. All right, so I think that's it for the lecture portion. I'm going to stop the recorder.